was right after all, although in a slightly more exotic context than he had envisaged. Tom, over to you.
Thank you, Keith. Well, it's great to be spending a semester in Cambridge and at the Isaac Newton Institute. And I want to thank Keith especially and Conrad for putting this program together and doing the lion's share of the work. So what I want to talk about is, glue balls and tight knots. And so before doing that, I'll spend a little time just reviewing. And since it's a mixed audience, I need to say, a few general things. So that's what I need. So there's a number of physical systems where you can have knots and links, and this includes biology and other sciences, mostly in physics. And so we're going to be mostly interested in tight knots. So I'll say a bit about tight knots and knot theory in general, but nothing profound, and then go on to tight knots in QCD, which is the main topic. There's also some other possible applications of what I'm going to talk about, but I'll maybe mention a few things as we go along, but give you maybe some just sampling. So, as I said, there's many potential systems with knotting, and examples are plasma physics, but also biology, where DNA can be knotted. There are even organisms that can knot themselves, macroscopic organisms. In quantum physics, we can have flux tubes, and they can be knotted, and they can be tightly knotted. So again, that's our main topic. But this can happen in QCD, but it can also potentially happen in superconductors. Superfluids we've seen that you can have knotted vortices, but those are not tight. Atomic condensates are another example where there might be tight knots and even cosmic strings. And of these tight knot cases, there's a universality class that I'll mention that at the end. So if you have, say, magnetic systems, plasma physics, and flux tubes, they're under tension, they want to contract. But if there's some topology to them, then there's a limit to how much they can contract and conserve that topology. And when the topology is helicity, magnetic helicity, then you wind up in tight configurations, or you end up minimizing the energy and holding the helicity fixed. Now, this differs somewhat from QCD in that there's going to be some radius of flux tubes held fixed. So the founders of this study in plasma physics include Keith. And here's a picture of some plasma. This is just 4 pictures of the sun with various prominences coming off the sun. And you can see that these magnetic lines of force can get twisted. They can also wind up being linked. And you can even have helicity in the solar wind that then interacts with the Earth's magnetosphere and changes helicity and so forth. These are not tight states, but they are examples of helicity. So what's the helicity? It's integral of magnetic field dA, where, this should be B dot A dV. That's Well, in forms, it's okay. So that's the helicity. Here's the magnetic energy. And if you hold this fixed and vary the magnetic field, you'll wind up in one of these force-free configurations where you satisfy something like a Beltrami equation. Now, what happens is that we're conserving some sort of quantum numbers. So helicity you can think of quantum number, but there can be other more complicated quantum numbers associated with higher order linking. So helicity is associated with Gaussian linking. And so if you just have a hop link, that's Gaussian linking, but you can also be self-linked the way the trefoil knot is self-linked. The first place I read about tight knots was in the biology literature. Andrei Straziak and his group wrote some papers in the late 90s. Even though DNA can't be in a tight knot, they were still interested in tight knots for reasons associated with DNA. And at that time, there were only just a handful of tight knots known. So here's an example of knotting in DNA. The first occurrence of knots in particle physics was when Lord Kelvin suggested that elementary particles could be knotted fluid vortices in the ether. And so Keith is not the first Scottish connection with knotting and linking. It goes back to Lord Kelvin. And then with discussions with Tate, the first knot classification was carried out by Tate, and we saw his picture in Edinburgh, sort of glowering figure, but he wasn't always no fun because I think he was an avid golfer. So we're going to move on now to flux tubes and quantum chromodynamics. And the model is glue balls as tight knots and links. And here we have quantized flux. And we're going to be interested in the energy of the knot. And the energy is just going to be associated with mass per unit length in these flux tubes. This is going to be a semi-classical model. So it's not a full quantum model, since for instance, we can't solve the confinement problem in QCD. So it's more on the order of, say, the liquid drop model, or another QCD model of this type is the bag model. So it's going to be associated with the bag model. So before going on, again, since it's a mixed audience, I want to say a few things about QCD. So QCD is the theory of strong interactions. It's an SU3 gauge theory, and that means it's a principal SU3 bundle over Minkowski space. The gluons live in octets, and which is the adjoint representation. The quarks live in triplets, which is the fundamental representation of the theory. And there's a Lagrangian that looks like F mu nu, the way it does in electromagnetism, except there's an extra gauge index that I've suppressed here that runs from 1 to 8. There's a topological term, or often known as the instanton term or the theta vacuum term. That's not going to come into play here. Usually this is very small. It's been shown that theta's been shown to be small. And then there's the interaction between the gluons and the quark. So psi is a quark field, and in the covariant derivative, lives the gluons.
You want to say, what's the tilde over the second? What's the tilde over the second F mu nu? What
That means dual.
Dual.
Yeah. So this is F wedge star F. This is F wedge F.
Excuse me, Prof. This last bracket, the beta mu d mu is just a Dirac function.
Yeah, these are some Dirac matrices. Probably better to write that as in Canada. So I'm sure everybody's familiar with QED. So let me compare QED and QCD. So in QED, the photon interacts with charged particles, say the electron. In QCD, the gluon interacts with quarks in a similar way, but what's different is because of the non-abelian nature of the theory, you can have gluons interacting with gluons. So there's 3 gluon vertices, 4 gluon vertices in the theory. And that makes the two theories profoundly different since this self-coupling leads to confinement. So it leads to a growing coupling constant at low energy. And so on longer length scale, the coupling goes up and particles are confined. So they're asymptotically free, which means at very high energy, the coupling's weak, but at low energy scales, the coupling's strong. So we never see gluons and quarks individually because they're all confined. So if you try to see individual one, it'll always pair up with somebody else. So this summarizes that. So at a high energy scale, 100 GeV, alpha sub s, which is the fine structure constant, analog of the fine structure constant for QCD, is about 1/10. But if you look at a low energy scale, around 1 GeV, alpha sub s is going to order 1. So the theory becomes nonlinear. That confines the quarks and gluons, and they get confined into some sort of bag of different vacuum from what's outside the region where there's quarks and gluons. So they can be confined in bags or in tubes, and the tubes are what we're interested in. So what we want to do is find these particles that are called hadrons that are confined to these bags and tubes, and you do that in particle physics experiments. So here's a typical experiment from Fermilab where there's a top quark in the picture here somewhere. And so a collision like this, you can hope to reconstruct the tracks of all the particles, extract the particle masses, and show that there's a top quark. Here's a nuclear physics experiment, RIC, which is similar energy, and you see that it's much harder to reconstruct something like this. So that these particles are detected, the ones we're interested in are in experiments like this, and actually lower energy than this.
What are the distinct lines in the nuclear?
Say again?
In the RIC experiment, there seems to be distinct radial lines where there is nothing happening. Is that the detector or?
Yeah, these are just particle tracks.
But there are about a dozen.
It's a big splash.
The question is why there are dark spokes.
Yes, about a dozen.
Oh, that's the detector is segmented, and so these are blind areas. Well, you can see the segmentation of this experiment too. So all these big cylindrical experiments have to be segmented. They're just too big to make single piece. Okay, so the flux tubes we're interested in are those that you get by pulling a QQ bar pair apart, quark-antiquark pair, and between them there's a flux, but unlike pulling a E plus E minus pair apart, the flux in this case is confined. If the flux tube is open, then it's a meson. Well, it's an excited meson if it's pulled far apart. If the quarks are close together, looks more like a bag, and then it's perhaps a ground state meson. In our case, we're interested in closed flux tubes because we want to knot them and link them.
Is the chromoelectric field, is it like the magnetic field?
It's more like an electric field, right?
Electric.
Because if I took an electron positron and pulled them apart,
The ends of the two.
right, then I have plus and minus charges, and
Yes.
you've got it. So it's more like confining that.
It's got a divergence, non-zero divergence.
Right, because you have sources.
Yeah.
I thought Keith's point was that when you close it, then the sources are gone, and it's more like a chromomagnetic field. I thought that's what you're.
Yeah.
Well, so this is going to be more in like a solenoidal configuration. You pull the QQR pair apart, and then you annihilate them into a loop, and then you've got a ring of this stuff.
Yeah, and then it's like magnetic field.
Right. Yeah. Then it looks like a toroidal magnetic solenoid, but you could conceivably have chromomagnetic flux too. But the ones you get this way are chromoelectric.
It's a vector field.
Yes. Yes.
The energy is also square of it.
Mm-hmm. Yeah. So yeah, just B squared plus C squared, where B and E get an extra index now that runs from 1 to 8. Because there's 8 gluon fields as opposed to a single photon field.
So what do you do with this index? You sum over it.
You just sum over it. Yeah. Yeah, because the Lagrangian has to be, well, terms in the Lagrangian have to be singlet. And
But I guess the energy is not a square, it has quartic terms as well. The energy is not simply square, it has quartic terms as well. It has fourth power of the E.
well, in this,
Yes, because you just gave a definition of the tensor, the field tensor.
well, there's extra non-abelian terms in the Lagrangian.
Yeah, so when you square that, you get quartic terms.
But those are interaction terms. They wouldn't be energy per se.
No, those quartic terms you mean in gauge potential.
Yes.
Correct.
Yeah.
But not in electric and magnetic field. So just like Maxwell theory, you still have
Yes, yes.
quadratic and gauge.
Yes, got it.
Okay.
Oh.
So here's a picture of a type knot. This is taken from Eric Rodden's webpage. And these were calculated with Ridge Runner, which Jason spearheaded. And I'll give you a better rope length for this thing. So that's the length for unit radius. And there are lots of these. So again, if you assume the radius is fixed, then you measure the length when it's tight, and that's this number, the rope length. So there's lots of pictures of these things. You can look at Eric's webpage. Now, if we look at knots, what you find is that as the number of crossings grow, the number of knots grows very fast, like exponentially. I'm not sure it's not a power law. It's very fast. And these are just prime knots. There's composite knots, and then we're also interested in links and composite links. So by 10 crossings, you've already got 165 different knots. And the length of these knots, the rope length, typically grows like crossing number. So the number at any given length is getting denser as you go.
Excuse me.
Yeah.
What prevents them from reconnecting? As you
Reconnecting.
What prevents reconnection?
Well, these topological quantum numbers, they will reconnect. None of these objects are going to be stable, but the topology will make them metastable. So at least it'll hold it up long enough that you can measure their mass, is the idea. So there's prime knots are what knot theorists studied first. but physics should allow any type of knot. There should be unbiased. So there's also composite knots. So for instance, if you take two trefoil knots, if I break them both open, paste them together, I can either get a square knot or a granny knot, depending on whether they're both left-handed or if one's left-handed and one's right-handed. So those are composites. And then there's also prime links. So the simplest example is the Hoff link, but then you can also have composite links that you can construct in the same way by this connected sum process. Okay, so now back to physics. So besides the standard hadrons, which are mesons and baryons, so mesons are QQ bar pair that are confined in a bag. Baryons are 3 quarks confined in a bag. We can also have various other possibilities. For instance, you can have things called hybrids, which are QQ bar pair with a gluon stuck in, or exotics, which are 4 quark objects or 6 quark objects, or maybe molecules where you have roughly 2 pions stuck together, or 2 mesons of some other type stuck together. And then there's glue balls, which have no valence quarks, right? All these are valence quarks. So if I have a pion that has a quark and an antiquark inside, we can call those valence quarks. So glue balls don't have any valence quarks. So there's some other type of object like a flux tube with no ends. There's more technical ways to phrase it, but that's probably sufficient for our purposes. So, sure.
You call them glue balls.
Generically.
Okay. And then you immediately jump to tubes, but is there a reason why you expect them to be toroidal as opposed to higher genus handle bodies? I mean, it's just the place where the concentration of the chromo energy is.
Yeah,
It's a little ball. I'm sorry, but why isn't it not why is it a tube as opposed to a more complicated?
Yeah, if you try to make something like that tight, you can always eliminate the vertices.
The question is why it has to be a donut rather than a pretzel.
Right.
Thank you.
Well, not a pretzel, but like a handle body. So two donuts just stuck together with the.
Yeah.
Yeah.
But you can eliminate that center vertex by pushing it around. So I can squeeze one of these down. Well, you also have charge conservation to worry about. So you flux conservation. Okay, so these hadrons have strong interaction. The glue balls are hadrons, so they have strong interactions. There's no valence quarks, and they don't decay directly to photons because there's no valence quarks. There's no coupling direct to charge. The way they would decay is, well, one is you can just break the string. So if I have one of these loops, I can break it and then back to a standard meson. I could, if I have a link, I can reconnect and then have no topology, and that could collapse. Or I could just quantum mechanically tunnel off and get rid of the topology. So that's the 3 ways that these things could decay. So here's a summary of the assumptions in the model. So we're going to make a one-to-one correspondence between these tight knots and links and particles called F states, and these are states that are normally thought to correspond to glue balls. And well, they're, how to say, there's, well, they have the right quantum numbers, and they typically are, well, they're just the states that are normally identified with glue ball. So we're going to, but usually glue ball models will have maybe 1 or 2 glue balls in it. We're going to take all these F states. We're going to have flux that's quantized 1 unit of flux in each tube. And these knotted and linked tubes are going to be stabilized by their topological quantum numbers, which means linking numbers, or which is a generalization of helicity.
Would you assume flux quantization? Why should the flux be quantized?
Well, yeah, it's confined into tubes, and if you make it from a QQ bar pair, it's just like if you made something from a E plus E minus pair. You would get a quantized amount of flux depending on the charge of the particles. Or the same way that confined magnetic flux is conserved in a superconductor, right?
Yes, that's right.
So it's behaving like a superconductor.
So you are assuming that the vacuum is a superconductor.
Yeah, well, a chromoelectric superconductor in this case.
Yeah.
So these states have angular momentum, but we're assuming that it's intrinsic angular momentum, not some type of orbital angular momentum. The flux tube diameter, we're assuming to be on the order of 1/10 of a Fermi. So I'll justify that in a moment. And then we're assuming that the configuration can relax into a tight state faster than it decays. So it relaxes and shakes off energy and gets into a tight state quicker than it loses topology. And this is very much like the case of magnetic helicity. So it's just the same type of assumption. So just a word about this assumption for this radius. It's associated with getting the proper string tension. So if I pull these things apart, there's a tension, and that's a force, which is the energy per unit length. And what we're going to measure for the energy per unit length, I haven't shown that yet, is about 65 MeV. So if we assume that the energy is 65 MeV, that the length that we're talking about is 1/10 of a Fermi, then using this relation, h bar c is 100, well, it's about 200 MeV Fermi in natural units, which is 1 in particle physics language. If we plug that in, we get the square root of the string tension, and is about 360 MeV, and that's in agreement with lattice calculations. So we're trying to make sure we agree with
What is Fermi in 10 to the minus what?
10 to the minus 15 meters.
15.
Right. So typical hadron size is on the order of a Fermi. Element depth, protons and pions and so forth. So here's how we make our identification. We identify the lightest one of these F states with the shortest either knot or length. So we identify what's called the F naught 600 with the Hopf length. We identify the next guy, which is the F naught 980 with the Treff, and so forth. So match them 1 to 1. And we try to match everybody that we can. Roman and I started this work about 10 years ago, but shortly thereafter we got in touch with Jason and Eric Rodden because we figured out that they were figuring out how to tighten knots, and so we've been collaborating ever since, and we're finally refitting all the data right now. So we've got something just about to be finished. So this refit is going to involve new glue ball data, which has been accumulating over the last 10 years or so. People have just been reducing the error bars. There's 1 or 2 new states, but there's not much change over the last 10 years. But the knot side of the equation is very different. So there were just a handful of tight knots and links when we started. Now there's close to 1,000. So these guys have, this Bridge Runner program can calculate everything up to, well, as far as you want to go until you run out of computer time. So they've got about 1,000 of them so far. And what's new in the table are composite knots and links that they're just coming out within the last few months. And that's the sort of the last part of the puzzle that we needed to put together so we could do this refit. And remember that as you grow in crossing number, the number of knots and links is getting dense as far as the length goes. And so by the time you get to identifying things, particles that would be on the order of 3 GeV, the number of knots and links almost looks like a continuum. So here's just, well, this is a list of knots and links from about 5 years ago. You're not meant to be able to read it, but just to show you how many new cases have been coming out, this is only up to, well, it's up to 8 crossings. And so what we're trying to do then is fit these glue ball masses, and what's shown here are the mass, which is the dark line, and then the width of this is the error bar on the mass. And we're trying to fit that with knot and link lengths. So we want some fit that goes like so. And continuing the Scottish connection, this looks to us like a tartan, so we called it the glue ball tartan. So what we're doing is we're trying to fit something that looks like a rather sporadic set of numbers, these f sub j state masses, with another rather sporadic looking set of numbers, which are these knot and link lengths. And what we'd like to do is match them. And if we do that, there's only a single parameter, right? We just have, well, there could be more, but we would hope to match it with a single parameter, which is the slope of the line along which you match. You could have, say, add another parameter which would add an intercept, so it would be an offset at the origin. Not quite as nice, but you could do it. So here is a 1-parameter fit for the lengths against the masses of these f sub j states.
So if you thought about it as 2 barcodes, the freedom is stretching and shifting.
No, well, yeah, if you have 2 parameters, but with 1 parameter, you just get to draw a line. So it's just the slope.
It's just stretching.
Right, so, yeah, so if you have 2 parameters, then, yeah, I could offset it like this. But this is for 1 parameter, you got to run through the origin, so it's just the slope. So you just find the best slope.
Well, maybe you should say why we want to have linear.
Why through the origin?
Why, why energy should be proportional to the length? You didn't mention that.
Oh, well, if I have if I have a flux tube, then each unit length should have the same properties, so you can let a mass correspond to a unit length. So it should be linear. Is that what you mean, Roman, or did you want to say something else?
That related to the Lagrangian which you showed before, and using Lagrange multipliers for conserved helicity, you can show that the solution to the constraint problem is exactly that energy or a state is proportional to the length.
Okay.
Flux tube.
Okay. So either way.
Yeah, minimizing length for fixed helicity or topological numbers is equivalent to minimizing energy. So
Well, but there
Right.
is one assumption here
Yeah,
that
there is an
the
assumption.
tube is assumed to have very low curvature. So we assume that the field is uniform across the cross section,
Mhm.
which would not be the case. Tom will tell later about the corrections due to the curvature
Yeah,
corrections.
right.
So, but in that simple assumptions, you expect it linear dependence. That's why he's fitting to linear.
Mhm.
But you're also assuming that the tube doesn't have any elasticity energy, so because you're really knotting it, and that would have a lot of energy if it preferred to stay straight. Is it right?
Well, I'll say more about that. Well, at least about the bending. So the bending's going to play a role. So one difficulty here is, well, let me first say that, so the error bars this way are the errors on the mass determination of these states. The error bars this way we put on, that's an error in the length, but not in these uncorrected lengths. That will be an error that will show up in a few minutes. So if I remove these mathematical errors and just keep the physical errors and look at these 2 points, then these guys are known to 1 or 2 MeV. So they're, in that sense, they're very far off the line. So these are very bad for the fit. We pay a big penalty in chi-squared for those. Oh, and one more thing, this state,
Which fits with that question, doesn't it? Because there are few crossings that curvature is high.
right. So we're going to make curvature corrections. So this state, which has been in the particle data table forever, used to sit right on the line with a much bigger error bar. They just refit the data within the last few months, and they've moved it down here. So that's not so bad because it's like 2 sigma off the line. Because it still has a big error bar, but the error bar used to be like this.
This is the hot link.
That's the guy we identify with the hop link. And this is the guy identified with the trefoil and so forth. So here's what happened. So before it was called the F0 600. It's also, well, the earliest designation, or people used to call it the sigma, but then when they systematized things, they started to call it the F0 600. That actually was at 800 MeV plus or minus 400, so giant error bars. And this is because that mass was extracted not just from some simple invariant mass plot, it was extracted from partial wave analysis. But now, since they've done that analysis better, they've even renamed it, and now it sits down here at 475 with a much smaller error bar. Now, there's another state that's treated in a similar way. It's the F0 1370. So it's going to come into play in a few minutes. One thing that could have, well, that can drag states down are mixing with other light states. So, yeah, so that was a comment about this fellow. So now what we can do is look at these tubes as physical knots, not just as ideal knots the way a mathematician would look at them. And so if we have a straight tube, as Roman mentioned, the flux should be uniform across the cross-section. But if we bend the tube, then that'll no longer be the case. So again, you can minimize the energy in the tube for a bent piece of tube. So we're going to correct the energy per unit length in the case where the tube is curved. So the way we do that is we assume that the flux, the total flux going through the tube is constant, but minimize the energy. So we do some variation. So here's the picture. So if we take a toroidal solenoid. Here's a slice of it. Here's the center axis of the donut. So the donut's doing this. And so we've got a large radius, R2, and then the radius of the dough of the donut is R1. So this variation, we vary B and find that the magnetic, well, this is just a magnetic example. So the magnetic field would fall off like 1 on radius. So we can get the energy in such a donut. And the form of the energy looks like this and the total length is 2 pi r. So if we compare that to a straight cylindrical piece and calculate its energy, it has this form. And so the correction, how this corrects the straight piece, looks like this. So as I take the radius and shrink it down to where there's just a point in the middle, so I shrink the hole in the donut to a point, I get here, because that's where R1 and R2 are equal. So it can correct it up to a factor of 1/2. Now, what we do then is, for any of these knots or links, slice them into pieces of toruses and then calculate the energy for each one of those toruses and paste them together to make the knot or link. One example where you can do this exactly is, well, this is a chain of 3. So so it's 2 Hopf links hooked together. So what I have there is 2 donuts and then 1 guide that links the 2 together. So I have 2 circles and 1 racetrack in the middle. So the racetrack has 2 straight pieces. That's this part. And I've got 2 circles, 2 semicircles. That makes 3 full circles. That's this. And then this is the correction. So if I look at the correction to its initial length, which was 6 pi plus 2, this correction reduces things to 93% of what they were before. So it's an effective reduction of the length, or energy per unit length, if you want to think of it that way. So for the first 72 knots and links, these are the overall corrections. So there's roughly, well, a little more than 8% correction on average, but you can see that there's a spread in these corrections. If you fit the first 945, it looks a bit smoother, but still the corrections are roughly in the same area, 8.5% or so. So we include all these and refit it again. What we'd like is a linear 1-to-1 fit between masses and lengths, but we do have some options. So the guys with big air bars we can move around if we can improve the fit by doing that. And so we would do that in order to, say, account for some tension in the data, and by leaving gaps here and there. And then search for the best fit. So here's sort of a flow chart of where we're going. So we were looking at these uncorrected lengths. 1 parameter fit wasn't very good if you look at the chi-squared, because some of the very tightly constrained guys were off the line. If we do a 2 parameter fit, we'll see that that doesn't help much either. But if we look at the curvature corrected case, then we get a much better 1 parameter fit. And then once we have that, there are 2 of these options where we can, this is the state that we can move around, the 1370. So he can be fit high or low, and I'll show you what that is. And in one case, we get a 1-to-1 match for the first 12 states. In another state, there's a gap, and we identify that with a prediction. So here's the 1 parameter fit. where this guy is fit high. Now, even though he's pretty far offline, that's only like 2 sigma away from the line. So it's not that bad. I mean, if we put, these are the guys that were causing trouble before. We can't have those far off because they had tiny error bars. This guy has a big error bar, so he can come farther off the line and still get a good chi-squared. Right, so these now have moved onto the line with the curvature correction, which is good news. And this is quite a good fit. There is some tension in the data around 1200 MeV, so there may be a state there. I'm not going to show the details of that, but if that's the case, then that allows another state to be identified and for us to fit it. So that means that there's an unused link that could be identified with a state in this range, and if this previous fit would put it at around 1190 MeV. And just to give you an idea of what the data looks like, here's a single state, the F naught 1710. This is more or less typical. This is about half the experiments that have been done on this guy. These are the mass determinations by these experiments. And this has been, you know, this goes back to 83, but people were looking at this longer. So there's many, many experiments over many years that have looked at most all of these states. And here's an example of some of that tension in the data. So if you look, this mass determination is pretty incompatible with this guy, 3 or 4 sigma. And maybe, well, you can look at any pairs. This is a tight determination, so this is not in very good agreement with that. So there, and this is only this collection. And this runs across most of these states. So the math determination is, you can fit a central value, but the fit is not typically good. So let's go back to our 1-parameter fit with this high 1370 arrangement. So when we do that, these are the states, and we fit those to knots and links. Here are the knots or links that have not been identified. So there's one guy down here, and then up here there's quite a lot. So we match them all. Well, let me just show the full collection. So we match everybody till we get up to here, which is around 1700 MeV, and then we start to have more glue balls and states, but you expect that. Eventually we run out of particle physics data, but knots go on forever. So that's not so bad. Oh, and here's the chi-squared. Now that's assuming a 3% error on the lengths. And that I think is conservative, but that's one last thing that we need to sort out. The slope is 65 MeV, should be MeV here, and we've got one low mass prediction at around 1200. That's this fellow.
What knot? Is that the figure of 8 knot?
I think it's the 4-2-1 link. So it's 4 crossings. Yeah, it's not the hop, but it's the next guy. Okay, to summarize then, these two states that were close together, that were very tightly determined, they were the F1270 and F1285. They were poorly fit when you don't correct the lengths, but they improve dramatically when you do curvature corrections. So if we return again to these uncorrected lengths and do a 2-parameter fit, we can improve the fit of these tightly constrained guys, but at the expense of introducing an intercept, which is not particularly good, right? Because as you shorten the tube, you would expect the energy to go to 0. And that's not what happens here. When you run out of tube, well, you cross 0 energy clear over here at some negative length. So so even though you can improve the chi-squared a bit, there's still a fair amount off the line, and you introduce this intercept. So that's improved. This is a problem, maybe an indication that, again, that we need to do the curvature corrections. And if we do look at the curvature corrected 2-parameter fit, then it changes very little. And the good news is, even though we introduce an extra parameter, which is this intercept, we still go roughly through 0. So that does have good behavior. So these guys are, the tightly constrained guys are still on the line, and the intercept is much better. So again, curvature correction wins in this case. And here's a summary of that. So the 2-parameter fit doesn't do well for the uncorrected lengths, but it does quite well in the curvature corrected case. Now, there's other possible corrections to put on here. So you can have constrictions of tubes, right? If I take a straight tube and put another one around it, the tension in this guy will squeeze the one in the middle and collapse its radius a little bit. And we've done an estimate for that, and that should be roughly a 5% correction for a Hopf link if it behaves like magnetic flux tubes. So there can also be QCD confinement effects that we haven't taken into account because we don't know how to do that.
What's the order of magnitude of the radius of these tubes?
1/10 of a Fermi.
That one, oh, yeah, that's the 1/10.
Yeah, that's a 1/10 of a Fermi.
Mm.
So here was a picture of that. So this, well, I'm not sure you can see it, but this region is shaded. So if we've got a donut again, but a tube going straight up the middle, and this guy's trying to squeeze this one, the magnetic pressure in the guy in the center is pushing back, and so it comes to some balance, and it's roughly a 5% correction if you add it over the Hopf link. Another possible correction is if I just take a tube and wrap it around another tube, or it's like wrapping a tube around, or a rope around a post. If I pull on it, I'll distort the cross-section. So that, again, should be probably a few percent. So these are corrections away from the ideal case. So we already have these curvature corrections. Even though the overall correction was about 8%, the variation is what really counts, and that was about 1.5% or so. And we expect something similar for these constrictions and distortions. And QCD effects, we don't know. So we'll just take these, and that was our estimate of error on the lengths of around 3%, which I think, again, is conservative because we don't know how to put these on. So, and again, to emphasize, only the spread in these corrections is important. So if everything was corrected in the same way, it would just shift the overall slope and not change the fit. Well, it wouldn't change the chi-squared of the fit. So here's the fit with this F1370 identified with this 421 link. So instead of fitting it up here, we can fit it here. This is somewhat better. This is maybe, well, it's only roughly 1 sigma offline. So the chi-square gets improved. And it's our best overall fit. And we match the first 12 knots and links with the first 12 of these F sub j states. Here's the 2-parameter fit again. Well, so this is a 2-parameter fit for this low F1370 identification. And again, it runs almost through the origin, so that doesn't cause a problem. Now the predictions don't start till around 1700, and notice that there's a clump here, a little spacing here, a big clump here, and if you keep going, it just goes wild. And here's a summary. So the chi-squared here is 28, but again, there's a lot of tension in the data at these various points, and if we broaden the mathematical error a little bit, we can certainly reduce this. So it's just a matter of determining what corrections to put on. The tube energy is against roughly 65 MeV, and there's no new states below, well, I guess it's 1690. So here's, I guess that's the 1710. So there's a few states down below it. And then we get lots above it. So this is curvature corrected 1-parameter fit. So that's our best fit. And we would argue, since it goes to the origin, we don't need 2 parameters. The real model should just be 1, but it was just sort of a straw man to check things. There's a summary. Well, we also measure R squared, and we can compare this energy with lambda QCD, and not the values themselves, but the quality of the determination. And we can determine this to about 1.5%, where lambda QCD is typically determined to 5%. So we think this is probably a good length scale to use in QCD. Here's a summary of the 2-parameter fit. So the intercept was at 19, but plus or minus 100 and something. So it's certainly very consistent with 0. You can also look at p-values, which measure quality of fit. So there's various goodness of fit tests and variance tests, and any p-value greater than about 0.1 is very good agreement. So all this is in good agreement. So I'm not going to go into details on that. I think I'm out of time already. Sorry. Here's what I haven't given you numbers, but here's finally some numbers. So here are the states that we're fitting. And here's the particle data table mass. Here's the knot or link that we're identifying them with. And here's the curvature corrected length of each of these guys. And here is the energy in MeV that we predict for these states to be compared with the measured values. And there's more stuff below the bottom here. This is all I could fit on the slide and hope that it's legible. So what we have is no new states in this best fit, this low 1370 fit, nothing below around 1680 or 1690. We have 5 new states between 1690 and 1705, and then lots of new states above 1720. And we're estimating the errors around 3%, but that may be subject to some minor changes. I showed you that there's tension in the data around 1710. that tension could mean that there's multiple states there, and that could fit some of those predictions. Also, there's a state at 1810, there's tension around that one, and various other ones. So there could be, instead of a single state, multiple states that would fit with what we've been looking at. And I want to emphasize that there's 50 years of high energy data that has to be reconciled here. And so the particle data group does that. They do a very good job at it, but it's still a complicated business. So there's multiple states possible in these regions, and it would be nice if people continue to work to resolve those regions. Now, I had some things to say about lattice, but I think I'll skip that and jump straight to the conclusion. So, if we look at quantum systems with knots and links, we can have flux tubes with quantized radius because of the quantized flux, and this will lead in the tight knot case to quantized lengths, which means quantized energies up to minor corrections. This should be true in any system where you have these quantized flux tubes. So that means there's some universality to the spectrum, and there's one universal parameter, and that's the slope. So that's all you have to determine for each of these systems. And in the QCD case, I just showed you that you can get predictions. So it would be nice to have other systems where you can make predictions. So I'll quit there. Sorry for going over time.
Yeah, well, it is wonderful to have a system where you make predictions. Have any of these predictions really borne fruit? I mean, do the particle people, do they take this seriously now?
I don't know. I haven't seen a paper about it yet. I'm still waiting. But we have taken it very seriously.
Yeah.
And have, well, this new paper I hope will energize them to look for something.
Yeah.
Sure.
Did you calculate any solution of QCD, even in classical terms, that gives you those knots?
Well, there are people that look at knots and sigma models and QCD, but you can't solve confinement in QCD. So to get these flux tubes to begin with, you need to solve the confinement problem. So there's no direct calculation in QCD.
So there's no numerical calculation or analytical calculation calculating those knots.
Well, that's the one thing I was going to say about lattice, is that you could potentially do this on the lattice,
Okay.
but you would need a much bigger lattice than they're currently using. So I've talked to lattice people. It's a problem that they haven't even tackled. So it's not an unsolved problem. It's a problem that they haven't even tried to solve.
Let's start here.
Oh, so in the particle data book, there is the catalog of these states, which are measured in colliders. So,
Well, they're not. They're measured more at low energy experiments.
but these
Now
are
it'll be
not
more like
collided
CBAP, where they-
simulations. These are actual states. These are not found in numerical simulations. These are
No, this is all particle physics data from the particle data group.
So what is their explanation of this state? Do they have a physical...
Well, they just collect data. So people have written papers on glue balls. And lattice calculations argue that the lightest glue ball should be about 1,500 MeV. But some people identify that with something called the F naught 1500, some people with the 1710, other people with lighter states. We've just been egalitarian and taken all these F sub j states and tried to identify them with knots and links.
Yeah, the question really is there any competing theory?
Yes. Do they have a competing explanation
Yeah.
for the physical nature? Is there a model for the states that is accepted by the...
Well, I don't know. There's nothing
So it's
accepted.
an unsolved problem.
Right. I mean, there are various models, but there's no model that is dominating.
No model.
Shahid.
Very wild idea. Is it not possible that the energy goes to zero for a finite tubelet? Your data suggests that there could be a bend at the bottom, something like a minimum length of rope before you have finite energy.
Or before you have zero energy?
Yes.
It's like the length is quantized in a sense.
So the
Well-
quantize and the minimum is not zero, minimum is some number. If you look at the data which you were fitting a straight line,
Right.
a square root seems to fit that as well, but it will depend that. But for that you have to make the physical assumption that.
Right. Well, then you need a model of why it would behave that way.
Mhm.
You would need some sort of model of,
Yes, you need some sort of model. So you could. This is just wild guess.
well, you need some different energy functional, or, yeah, you'd have to change.
Asymptotic freedom suggests that at very low, at short distances, you don't really have much energy. These things are free. So you need a stretch of a string before you need energy to form.
Well, it's hard to get a zero length string, right, or even approach zero. Well, first off, you'd have to break the closed loop and then let the QQ bar pair get very close to each other. But now you've got a mess on, so it would mix with that. So I think it would be very hard to sort that out.
I have N questions, but I'll try to keep N small. Okay. So question 0, the unknot is not there in the picture. I'm just wondering, that may be.
Well, it has no topological charge, so we're assuming that it collapses.
Okay, all right, but that is sort of the 0 point energy question that.
Right.
So
Right.
Next question, once you get up a little bit past, or even the trefoil, there seem to be other states of the same knot type, but that have the critical or even have the other local minima. And they occur within, I think, the 12 that you have. Jason probably knows.
Right, but, well, if I have a trefoil, since it is quantum mechanical, things are jittering, right? There's quantum mechanical fluctuations, and that should probably help the system find its minimum. So at least for the first, 20, 30 knots and links, I would hope that they'd all find their true minimum.
But let me make the specifics just on that, because there should be some fraction that's in one and the other. There's like a doublet or a multiplet state, and you might want to average the values depending on the probability that you'd be in one state or the other. I'm just saying that seems like something that might be reasonable to do to get a better fit of physical data. If they're too close by local minimum energies, then wouldn't you expect
Well,
the
yeah,
fraction to be
if they have the same quantum numbers, you would expect them to perhaps mix, and, yeah, but we haven't done that refined in analysis.
Let me ask the last one, because this is a shade of what I asked last time in another talk. The rest mass is invariant under the Lorentz group. That's for Jason.
Yeah.
Now he knows where I'm really thinking. Yeah, so
It's
when
the
you do an
definition of
experiment,
mass.
right?
Yeah.
I mean, I've got something that's in this frame, but when I boost it, it doesn't look like.
Well, all this is taken care of by the experimenters. I mean, not to worry about that.
Okay, thanks.
Yes.
So since you are using Yang-Mills theories instead of Chern-Simon, so could you cook up more knot invariance that's not a part of Chern-Simon?
Right, we haven't looked at Chern-Simons. That's, topology, topology and gauge theories are associated with Chern-Simons, but we haven't done that. We just assumed that you get some sort of solitons by tying these flux tubes into knots and links. So, yeah, so the full analysis would probably involve Chern-Simons theory.
All right.
You're calculating all these corrections, which are due to the either change of the cross-section shape or redistribution of the field
Yeah,
within the cross section.
Yeah, the only one we've actually done is the redistribution of the
Redistribution.
field.
But you always assume that the calculation of the energy is exactly the same as it would be in magnetic field.
That's right. Is that a good approximation? I would think so, but
It's linear, not nonlinear.
The question, yeah, because if you're looking for corrections which are of the order of 1% or 2%,
right.
now that assumption of how you calculate the energy, is that, is that not a bigger error than?
Could well be. I mean, there's going to be end effects when you get close to the boundaries of the tubes, and that's where confinement comes in. So there could be corrections bigger than the ones that we considered.
But the basic assumption that it's the integral of the field square, is that well established in the QCD physics?
Yes, I think so. Well, it in the theory,
Yes.
assuming that was like the right Lagrangian, then I would say that it's
So there are no corrections to that simple calculation coming from the theory.
Well, I mean, are there quantum corrections to that? There's quantum corrections to the gauge couplings, and so maybe by the
Conrad, there's a reason why it's called standard model.
Yeah.
It used to be a Sloan-Weinberg model, but now it's standard model. So
Right. So there is the formula for the energy. There's no it's beyond question here.
well, almost beyond question.
Very good. It's amazing to me, actually, that you can consider the redistribution of flux inside a quantized flux tube at that scale. But everything is, of course, on this tiny scale, so I suppose anything is possible. But it's it's a quantized flux tube, and yet you have structure within it, right?
well, that's what we're assuming. Yeah.
Oh well,
But the flux is still quantized.
the flux is still quantized.
Yeah.
yes.
So we haven't upset that.
Yeah.
Are we in thin ice? I don't know. But it does seem to improve things.
Yeah, it improves the fit. Well, it's amazing. I think Kelvin would have enjoyed this seminar. You've loved it. Thank you very much, Tom.
Thank you.